Who has not had the experience that queries suddenly return error messages regarding a deadlock and abort for no apparent reason? After restarting the query or the affected job, everything suddenly works as expected. If this happens only very rarely, then it may not be alarming. However, it's time to rethink your workload design if you regularly encounter deadlocks in your batch loads or reporting activities. In this video, you will learn what deadlocks are, how they are triggered, and how you can primarily prevent them. So that we don't just talk theoretically about deadlocks, I will also show you how to create one by yourself easily. Experimenting helps enormously in understanding the problem of deadlocks. So let's start the journey. By the end of this video, you will be an expert in dealing with deadlocks and no longer have the restart of the transaction or your job as the only tool to solve deadlock problems, but a whole arsenal of tools. Have fun. Deadlocks occur when each of two transactions holds the lock on a database object the other transaction needs next. Here is an example. Transaction 1 locks some rows in table A, marked in blue, and transaction 2 locks some rows in table B, marked in green. The locked rows of both tables are shown in red. The next step of transaction 1 is to lock rows in table B, and transaction 2 needs to lock rows in table A. We just described a deadlock situation. Without deadlock handling, both transactions would wait indefinitely and not finish. On Teradata, deadlocks can happen on one AMP, called local deadlocks, or across different AMPs, called global deadlocks. I will now show you an example of how a deadlock can occur. We will log in with 2 sessions on Teradata. Please make sure that autocommit is disabled if you log in using JDBC. Otherwise, the example will not work. The first session is logged on. Now we do the same for the second session, and again don't forget to disable autocommit. For safety, we check if we have 2 different sessions. This is important for our deadlock example to work. As you can see, we have 2 sessions with the numbers 1022 and 1021. In the first session, we start a transaction and perform an update in table A on column call 1 for the value 100. Note that we request a write lock on the whole table and do not end the transaction. In the second session, we start a transaction and perform an update in table B on column call 1 for the value 200. Note that we request a write lock on the whole table and do not end the transaction. Something went wrong here. One moment please. A syntax error has crept in somewhere. Okay. Now it works. Now we switch back to session 1 and try to select the value 200 from table B of column call 1. As you can see, the execution window appears, and nothing happens. This is because the write lock of session 2 prevents us from reading from table B. This is a typical situation. If we don't abort, the select statement from table B stays in the queue waiting to get access. Let's now switch back to session 2 and try to read from table A. By the way, you will have seen that we request a write lock for each statement to keep the example set up as simple as possible. I leave it to the interested viewer of the video to create additional deadlock scenarios. Please leave your ideas in the comments on this video. Both sessions are on hold. Session 1 needs access to resources from session 2 and vice versa. This is a deadlock. We will wait now for the Teradata Deadlock Prevention System to detect our deadlock. And here finally is our error message. As you can see, Teradata has detected the deadlock and returned error 2631, and terminated the transactions. I hope I showed you with this screencast how deadlocks work and how Teradata automatically detects and handles deadlocks. Luckily, Teradata uses a queuing strategy, serializing locking requests to minimize deadlocks. Table level and partition locking, a relatively new feature, are called proxy locking, and rows hash locking on dictionary tables is called pseudo-table locking. Without a locking strategy, and 2 transactions asking for a write lock on the same table, the first transaction could get the lock for the table on some of the AMPs, and the second query could take the locks on another set of AMPs. None of the transactions would be able to finish its task. Both requests would wait forever. By the way, a no-wait lock modifier is available, which aborts the request if the AMP can't obtain the lock immediately. The proxy lock or pseudo-table strategy avoids such deadlocks by serializing the requests. Many of you probably have seen the term to prevent global deadlock when explaining a query, which relates precisely to what we described before. Here is an example that shows the deadlock handling strategy in action. 2 update statements execute simultaneously, update 1 and update 2, and they want to update the same table. Each update intends to have the right lock. Pseudo table or proxy locking ensures that each request has to get the pseudo lock on a reserved row hash before obtaining the required lock. Proxy or pseudo table locking defines an AMP, the gatekeeper to the locks for each table. The gatekeeper AMP for each table is found by hashing its table ID value. Hashing is done in the same way as primary index hashing. By hashing the table ID, the gatekeeper AMP is found. As the hashing algorithm is stable, the row hash for a specific table ID always is the same. As long as the system configuration is not changed, there is a one-to-one relation between the table and gatekeeper AMP. In our example, two update statements want a write lock on the same table. Assuming that update 1 is slightly faster than update 2, it will get the proxy or pseudo table lock on AMP2, which is the gatekeeper for the table customer. Update 2 has to wait in the gatekeeper queue of AMP2 and will be next as soon as update 1 is finished and has released the write lock. Now let's move on to the options we have to reduce the risk of deadlocks. Teradata offers a few options that we will discuss. Use locking for access whenever dirty reads are allowed. This allows reading even if another transaction performs an update or insert statement on the table. Of course, this is only useful if the data does not need to be 100% consistent. Avoid begin and end transaction but use multi-statement requests instead to avoid table-level deadlocks. We have already seen the negative effect of begin transaction and end transaction and table write locks at the beginning of the video. It is better to use multi-statement requests. For unique index access, unique primary index, unique secondary index, use locking row for write or exclusive before executing a transaction. Row hash locking is the most granular way of locking and should always be used, if possible, instead of locks on the whole table. Teradata can upgrade to table locks anyway if it makes sense. In an application, we suggest putting all exclusive locks on tables and databases needed at the beginning of the transaction. If a lock can't be granted, use the no-wait locking modifier option to abort the transaction immediately. We have reached the end of this video. I hope you learned something new and can use it in your daily work with Teradata. If you liked our video and would like to see more or have any questions, please leave us a short comment. And please don't forget to give us a like if you liked the video. It's very important for us to get feedback to see if we should expand this video series. Thanks for your feedback. See you soon.